Today we'll be talking about linear regressions, which are a very powerful modeling tool that allows us to predict future data trends as well as analyze current data trends by determining a line of best fit through several pieces of data. Today we will delve into a little bit of the theory that falls behind linear regressions using geometric means and linear algebra, as well as doing a practice problem, going through it on paper, and then coding it using Google Colaboratory. So, to start off, let's throw some plots. So, over here, I have my y-axis. Over here, oh boy, my x-axis, label. And with this, I'm just going to throw on a few random plots. So let's put one there. We'll put, one here, one there. Now, if you were to go to Excel and ask Excel to do a linear regression of this plot, you might end up with something like that. This is Excel's idea of what the best fit for this data set would be. Let's go ahead and throw some numbers on these. So when Excel does a linear regression like this, we'll call this 2, maybe 2.8. Essentially what it is doing, it is looking at your data set and it is adjusting its own line of best fit to minimize the amount of error it has between the data that you have given it and the line that it creates. So when I talk about error, I'm talking about the deviation from the best fit line. That is error, and it accumulates, and that value is what determines how good of a fit this line really is for the data set. So let's finish labeling this. Call it 1, 1.8, and maybe like 3, something like that. Right? Now, going back to some elementary algebra, we know that straight lines have this equation form, y equals mx plus b. The y is equal to the slope times the x value plus the slope intercept. Or rather the y-intercept, not slope-intercept, sorry. And we can model this in a very similar fashion using some linear algebra. So if we look at the y values we have here and throw them into a matrix, we see that we have 1, 1.8, and 3 labeled on that y-axis. Now, you look at this and you say, hey, well, if we looked at this from the perspective of having the best fit line, we are trying to model the line using these points. So these points are rather approximations of the best fit line. It kind of works two ways. So what we can end up saying is, well, we have these 3 values here, which essentially end up being the y values for our model. Rather, we're using these points to approximate our model. I know that sounds a little backwards. We're using the model to actually analyze the data points, but it kind of works both ways. So we can say that, these plots are somewhat approximate to our model. And essentially what we're doing is we're still following our equation up here. So we'll say that we have our slope times our x values, which were 1, 2, and 2.8, and then multiply that by b. And b will get a matrix of just ones, because b is not dependent on either x or y value. It is a constant as is defined by its equation. So now we have something that looks like y equals mx plus b. Y equals m. This is the x, if you can imagine it, plus b. Throw that up there, why not? These are the x values. So we're still following what basic algebra has taught us. Now, we'll follow a little bit of what linear algebra teaches us, which is we can rewrite this in terms of a matrix multiplication. So bring back y model. And what we're essentially doing is we're going to rewrite this equation as a product of two matrices. The first matrix, which we'll designate matrix A, is the design matrix. It is this matrix and this matrix combined into one. So 1, 2, 2.8 for our x, 1, 1, 1 for our intercepts. Boom, design matrix. What ends up getting left over are these m and b values. So we'll throw that into our coefficient matrix, m and b, here. And we'll just give that a label of c. That's our coefficient vector. Now that we have this, we can go on, take a look at maybe improving our idea of what a linear regression really is. So I'm going to redraw a plot. So we have a y direction, and then, yeah. So we have a three-dimensional plot here. So what I'm going to do here now is I'll throw out some random data vector, right? So we'll say that, okay, we have some vector. Oh boy, let me draw that a little bit better. We have some vector pointing to this data spot right here. So let's say like 2, 3, 1 is the value for this. And essentially what we're doing, I'm going to throw some values on here, or the labels on here, just so we know what we're looking at. What we're saying here is that we have some vector pointing to this data spot that we have defined. I want to approximate this vector. And the way we can approximate this vector, let's put that here, is through combining or approximating it by combining linear terms. So I'll show you what I mean by that. So we have our defined vector here, 2, 3, 1. Well, what we can do is we can combine something called the basis vectors. So the simplest basis vectors are the ones pointing in the x direction, pointing in the y direction. So we can create basis vectors based off of these two basis vectors. Or sorry, rather on these two directions. So let's say, so our basis vector for the x direction would be 1, 0, 0, x, y, z, just 1 in the x direction and nothing else. Our basis vector in the y direction is 0, 1, 0. And because we don't know by what factor, we'll just scale this by some constants. And this is a very intuitive way to think about approximating a vector. Now, if we were to follow our intuition, we would say something like, oh, let's just name values. Since we have 2 in our x column over here, we can toss 2 here, and same thing, follow there, toss 3 there. And again, this is very much just following intuition, because if we have 2 times this vector, 3 times this vector, add them up, you get a vector 2, 3, 0. So let me just toss like here, say that. This is 2, 3, 0. This is an approximation we have determined based on our basis vectors. Now, when we do this, something very interesting happens. As you can see, our approximation, we are trying to make it as close as possible to our data, to model something well we want to minimize the amount of error that we are creating. We will always have some sort of error when modeling data because data isn't always perfect and happy. There is always going to be some sort of noise. What we have essentially done is now we have created this error. If we were to move this point either there, upwards, downwards, we would be messing with the distance of this error, which is not something that we want to do. So we have chosen this bot based on our basis vectors because it does something very interesting. What it does is now we have created this approximation where the error is perpendicular to our data point. And this ensures, by definition, that we have the shortest amount of error possible. The distance here is the shortest it'll ever be because it is perpendicular. If we were to go a little bit more to the right or a little bit more to the left, a little bit more down, up, down, this would change the error and it would not be as good as if it were perpendicular like this. So this is the reasoning for using the basis vectors and the reasoning for why this creates the least amount of error possible, and that kind of leads into how we do linear regressions in the first place. So now that we've gotten a bit of clarification out of the way, let's go back to our original problem. Now, we see that when we are doing these linear regressions, we have our data point, we have what our model depicts as the data point or what it predicts as it. And of course, like we talked about earlier, we have some sort of error. Now, the error, we can rewrite it very simply as just the difference between the data and the model. As you can see, there's the data, here's the model, we have the difference between them, that's our error. A neat thing that comes almost with the territory of having this whole postulate where we have our error perpendicular to the approximation and minimizing that error. Sorry, the approximation perpendicular to the data set, which makes our error minimized, is that since we use these two basis vectors to make our approximation, and that approximation ends up being perpendicular to our data set, that means that these two basis vectors also have to be perpendicular to our error. So that looks a little something like this. So we have error perpendicular to, in this case, our first basis vector is our x's. So we have that is perpendicular to 1, 2, 2.8. And our error is perpendicular to our second basis vector, our intercepts, which is just a matrix of ones. 1, 1, 1. I forgot to do perpendicular. So now we have a couple definitions on how we can define the error. So something else that we can very quickly prove here. We have these two definitions for our errors. And what I like to do is I'm going to throw these into a matrix. Again, 1, 2, 2.8, go 1, 1, 1. This looks very similar to our matrix A over here, but this in reality is our matrix A transpose, which means that we've flipped the columns and the rows. The first row is not the first column. The first column is the first row. You get the gist. And what we're doing here is, wrong color. We're going to multiply by a matrix of the errors. So this is just our error matrix. We have 3 of them because we have 3 data points, 3 model values, 3 errors. It goes to show. So If we end up setting this equal to a matrix of zeros, this is going to be a 2 by 1 because we have a 2 by 3 here, a 3 by 1 here. The result of the multiplication of these two vectors, or these two matrices, is a 2 by 1 matrix. But if we were to do the dot product of this vector and this vector, and we find that our value is 0, this is essentially the same as this postulate that we had just proved or had just demonstrated a little while earlier. To say that when two vectors are dot product, and when you do the dot product, the value becomes 0, it is the same as saying that these vectors are perpendicular. So that's just a cool little thing that we can point out along the way. So now we get to do a little bit of fun stuff. So essentially, we can rewrite this out as if we have AT times the error, this is matrix multiplication, but I'll just write this in terms of algebraic terms. If we take our transposed matrix A, multiply it by our error matrix, equals 0, because, as you can remember, our approximation is perpendicular to our data point. Now, we know the definition of the error as y data minus y model, so let's also go that far. Let's make that replacement. So y data minus y model equals 0. Furthermore, we know that the y model is equal to our matrix A times our matrix C. So go one more step. Y data minus AC equals 0. Now let's do our distributive property. Transpose matrix A times y data minus transpose matrix A times C equals 0. And our last step, put these on opposite sides, and we get something like this. And what this achieves is now we have an equation that allows us to find our unknown values in matrix C. So now that we have gone over the theory behind linear regressions, as well as now we've derived a very helpful equation for us to find our unknowns in the coefficient matrix, we can go into a Python runtime like this, and we can write out some helpful code to calculate those unknowns for us. So far what I've done is that I've imported our libraries, NumPy, so we can use some functions, Plotly, so that we can graph it out. So first off, let's create a set of data. So let's define our x values. I'm going to use the linspace function, which will linearly space a set of data for us between a certain range. So let's say we want to go from 0 to 10, and let's say we want to have 21 partitions. 21, not 20, because if we have 20, that does not count 0 as our beginning point. It will exclude it and go to the first division. So we go 21, so it includes 0, goes to 10. You get the gist. And at the same time, we can create our function. And so a function might look like y equals 2x plus 1. So we have our x, which is our data set of unknown values, and let's just see what that is really quick. Right, so we see we have this array of evenly spaced values from 0 to 10, and essentially what we're doing is now we're plugging it into y, which returns these values according to our equation that we have written down here. So now we have our data set, and we have what it follows as well. So now that we have our data set, let's go ahead and graph it out. So we'll toss down something like fig equals make subplots, and we want to add a scatter. Where is it? Add scatter, and we'll say x equals x, y equals y, and I believe that's all we need to create. Oh, we want to make this markers. Mode equals markers. Right, so now we have our data. As you can see, we start at 0, 1, go all the way up. We have a straight line of data in a graph now. Now, if we really want to model what a real-world data set might look like, we're probably not going to get a very straight line like I've just created here. It will be a bit more deviated. There will be sources of error. You're not going to have this perfect plotted line out. So in order to kind of imitate what this might look like, let's update the definition of y a little bit. So we'll say that the new y values are going to have a bit of a normal distribution. So we can do that by using this random function that will either add it or subtract it by a random value according to our normal distribution. So this is our function for that. And so the first thing that we want to say, we're going to have that location equal to 0 because we don't want to change. We want the normal distribution to center around 0 so that we have some going up, some going down, not all of it really going up or all of it going down. We'll have the location set at 0. We will scale, and the scale is essentially our standard deviation. We'll set that to 0.75, something like that. And we'll say that we want the size of this. We want the size of this to match the size that we had originally in our y array. So that looks good. We'll update this, and now you can see that our graph is definitely not perfect like it once was. This is now definitely a bit more jumbled up, and so this is more realistic of what a real-world data set might look like, and we can continue on from here. Now the next thing we want to do is we want to start defining our matrices. So if we remember our equation here, we had our design matrix, and what we're going to end up doing is we're going to transpose that design matrix, and on the left-hand side, we're going to multiply it by our array of data values for our y, and on the other side, we're going to actually multiply it with our, we're going to multiply it with our design matrix. So it'll be the transpose times the design matrix. So let's go ahead and do that. Now, first off, we want to make our design matrix. We want to code that into Python. And if you remember, our design matrix was just our column of x's and then a column of 1s for the intercept. So the way we can do that in Python, so let's define our A matrix, our design matrix, and we're going to use the concatenate feature. So this is the syntax for the concatenate feature. And we said that we want one column of x's, and we want a column of 1s that is the same size as the column of x's that we have. We want the same number of 1s as we do data points in our x column. The way we can do that is something called np1s_like, and we just use the size of x as our reference. Now, if you look at matrix A, we have a beautiful array of all our data values from x and a column of 1s to accompany it. Now, we said that we wanted to use the transpose of our design matrix. And the way we do that is using this .t function, and voila, it is now transposed. So now that we have our transposed matrix, we can start solving as much of the equation as we can. So we remember on the left-hand side, we're just taking our transposed matrix, do a matrix multiplication with our array of y's, and we get this 1x2 matrix here. Now the other side, we have our transposed matrix times our original design matrix, so that'll look something like that. Now this is a 2x2 matrix, and that's important because when you do matrix multiplication, you want to have it in order so that the multiplication works out, and I'll show you what I mean in just a minute. Now we can start solving for our coefficient matrix, and the way we can do that is essentially we'll be solving both sides of the equation at the same time using np.lin alg solver. Now this is a very useful tool because essentially what we can do now is we'll toss in our multiplications for both sides. So this times this, and then this times this. Okay, I see my mistake. It's not solver, it's just solve. Boom, now it's happy. Now the reason why I pointed out earlier that the matrices need to be in order is, let's just say we did this as y, this is a. So now we're getting something that says we put in a one-dimensional array and the array needs to be two-dimensional. And that's because we need to put a first because we want to multiply a 2x2 by a 1x2. Or when we divide it, we are reversing the multiplication, so that we need to have a 1x2 times a 2x2. So that is the reason for that. So let's put this back to normal. And let's take a look. Now, if we remember, see, the first value is our slope, the second value is our intercept. So it looks our slope is something around 1.93, our intercept is something about 1.37. So that's pretty cool that we have that. Now, to do our linear regression, the last step is to actually graph out the best fit line. So let me quickly go back to my whiteboard. The one final thing that we can do here is my pen out. Cool. If we look here, we have a like term on both sides. We have the transpose A. If we were to divide on both sides by the transpose matrix, you just get the y data is equal to the design matrix times the coefficient matrix. And this is how we can get our modeling data, essentially. So let's go back to our collaboratory, and let's toss one more plot over here. So now what we're going to do the same thing. And this time, we're going to have our x equal to x. That doesn't change. And now our y is going to be equal to our matrix A multiplied by our matrix C. And since we want to do a best fit line, we're going to set this mode equal to lines. And now you see we have a linear regression with this best fit line that we have here. Like Excel, we have definitely sources of error, but as we had talked about earlier, this regression method uses the theorem that we have our approximations based on the basis vectors that make our approximation perpendicular to our data points, minimizing the amount of error that we actually see in our best fit line, which can be observed here.